Hi everyone, welcome to Data Hikes. I'm Mihir and we'll be going over the entity relationship model today. This will be the first in a series of database and SQL lectures that I will be covering soon. The first topic we're covering, like I said, is the entity relationship model. Let's begin with the purpose of the ER model or the entity relationship model. The entity relationship model is used to easily translate real-world systems in a relational or tabular format. So this basically helps us translate an idea or a concept of a database system that we have in mind in a format that would suit the relational or the tabular format. Relations and tables are used interchangeably in the context of databases. This is useful in building a database system without any technical knowledge or concerns. Now, when you're building a database system, an ER diagram specifically, you don't need to have any kind of technical knowledge, and obviously you don't need to worry about any technical roadblocks that may get in your way either. It is a concept, it's a model that you can draw without any knowledge of SQL or any concerns about what hindrances you may face. The ER model is also easily represented on paper using ER diagrams. So the ER model is a concept, ER diagrams are what when you put it to paper is called. But these two terms are often used interchangeably and will be used interchangeably as we move in this lecture. When building a database system, this method helps set a clear direction for writing the code. So what will happen if you have a database system idea in your mind and directly try to start and code it? You will run into conceptual and technical difficulties at the same time parallelly, which will be harder to navigate than usual. If you draw an ER diagram first, however, you'll kind of mitigate or get over the conceptual difficulties, at least for the most part, and you'll be able to focus more on the coding itself. So when you have an ER diagram in front of you for your database system, it really helps set up a very clear direction for writing your code. The diagrams are also very easy to understand and they're useful to explain a database system to non-technical users. It often happens that the stakeholders or the people that we need to present our database systems to are not very technically savvy. But for understanding ER diagrams, one does not need to be technically savvy. As long as they understand the concept behind it, it is good enough. Hence, these diagrams are also very useful in communicating a database systems concept to non-technical stakeholders. There are various symbols that go with an ER diagram, like we see here rectangles, ellipses, diamonds, lines, etc. And we'll get into what each of these mean as we move in this lecture. The first thing we're going to learn is what is an entity. An entity is an object that exists in the physical or conceptual form. An entity is most often represented by a table in a relational database. So this is really important to think about when you think about how an ER diagram translates to a database system. Whatever would be an entity in your ER diagram would most likely be a table in your database system. An entity, like we have mentioned here, is an object that exists in the physical or conceptual form, and we'll understand more of what that means when we look at some examples. So, the examples on the left are physical entities, and the examples on the right are conceptual entities. Some examples of physical entities are person, building, product, and vehicle. All these things are tangible objects that exist in the physical form, and these can be entities. Conceptual objects, on the other hand, are more like a company, a department, a school, or a course. These can have physical representations like buildings or, say, books in case of a course, but the ideas, company, department, school, and course are more of concepts than physical representations. Now let's see what a strong entity versus weak entity would look like. A strong entity can generally be identified by a key attribute. So there will be some identifier in that entity. So an example here is an employee. It is represented just by using a simple rectangle, and an employee is a strong entity because in the context of a company, an employee can be uniquely identified directly by their employee ID. So it's pretty straightforward. If there is something that can uniquely identify an entity, it is a strong entity. Now let's see what a weak entity might look like. An entity that cannot be uniquely identified by a key is a weak entity. It is represented by a double rectangle, as you can see here. An example here can be a dependent of an employee that may be a dependent in the context of taxes or insurance, but this dependent is not really identifiable in the context of a company without going through that employee. So, a dependent doesn't really have a unique identifier. They depend on the employee's unique identifier to be identified. Hence, because a dependent does not have their own unique identifier, it is called a weak entity in the context of a database. Now let's look at what attributes are. An attribute is a property that helps describe an entity. It is most often represented by a column of a table in a relational database. So an entity has attributes to describe it. Similarly, when this entity with attributes translates to a database system, the entity would become a table and the attributes would become the various columns in that table. Now let's look at a few types of attributes. The first is key attributes. An attribute that can uniquely identify an entity is called a key attribute. We kind of covered this when we looked at strong entities. This attribute will be called the primary key in the relational database. We'll learn more about the various keys that relational databases have, but for now, it's important to understand that the attribute that uniquely identifies an entity is the key attribute. The example can be the same again, where an employee ID will identify an employee uniquely. All attributes are represented by writing the word in the middle of an ellipse, like this here. But when you underline it, it becomes a key attribute. The next type is multi-valued attribute. Attributes that can have multiple values for a single entity is a multi-valued attribute. Storage of multi-valued attributes can differ between SQL platforms, and we can get to those topics as we come across them because it can be a little complicated sometimes. An example of a multi-valued attribute would be a single course can be associated with multiple departments in the university. This means if there is a course, say computer networks, it can be associated with multiple departments, say computer science and computer engineering within the university. So the single course can have multiple values for its department attribute, and it is represented using a double ellipse as you can see here. The next type is composite attributes. Attributes that can be broken up into multiple attributes are called composite attributes. An example is an address. An address by itself means something. It has meaning. It can help describe some geographical location. But the address can further be broken down into multiple smaller attributes like street, apartment, zip, city, and state. And all these also have their unique meanings. So when an attribute can be broken down into multiple attributes in a meaningful way, it is called a composite attribute, and it is represented like this with the main attribute, with the composite attribute at the center, and the parts it can be broken down into connected by it via lines. The last type of attribute is a derived attribute. As the name suggests, this type of attribute can be derived using a different attribute for that same entity. This attribute can coexist with regular attributes, but they can also be calculated using the attributes that they can be derived from. For example, in a table for, say, a course or examination scores of students, the grade can be calculated using a total score. Each school must have some formula, and let's say this formula in this case only depends on the total score. So, for example, a total score would be 95. The grade can be calculated using this total score, say, into a grade of A. Such attributes that can be calculated using other attributes are called derived attributes, and they are represented like this using a dashed line for the ellipse, as you can see here. Now we will look at relationships. A relationship depicts how entities are associated with each other and is depicted by a diamond and connected to entities. They are connected with solid lines, as you can see here. The relationships themselves are usually verbs, and they are read from left to right in an ER diagram. For example, the below relationship is read as a teacher teaches a course. Next, we will look at degrees of a relationship. The degree of a relationship means the number of entities involved in the relationship. The first type is a unary relationship. When only one entity is participating in a relationship, meaning the relationship is to itself, it is called a unary relationship. For example, in a company, a person reports to another person, and it can be represented something like this in an ER diagram, where only one entity is involved with the relationship. The second type is a binary relationship. When two entities are participating in a relationship, it is called a binary relationship. Again, the same example, a teacher teaches a course. And this is the kind of relationship that you will come across the most in an ER diagram, where there are two entities associated with one relationship. The third type is an n-ary relationship. When multiple entities are participating in the relationship, it is called an n-ary relationship. For example, in a school, a teacher teaches a course and a teacher also teaches a student. So there are three entities here: teacher, course, and student, and they're all related using one relationship called teaches. And both these lines of a relationship make sense. Teacher teaches course and teacher teaches student. Hence, because there are more than two, in this case three, entities associated with a relationship, this is called an n-ary, or in this case a three-ary relationship. Next, we will look at cardinality of a relationship. This basically means the number of times an entity set participates in a relationship. We can look at an example to understand better. The first type is a one-to-one relationship. When both entities can only participate once in the relationship, it is called one-to-one. For example, one school only has one principal, so one school is headed by one principal. A one-to-one relationship can be denoted by these little ones written on the lines between the entity and relationship. Just to check if this makes sense, can any of these be more than one? Can we say that one school is headed by multiple principals? That is not usually the case. That doesn't make sense. Can we say the other way around? Can we say multiple schools are headed by one principal? That doesn't make sense either. Hence, since only one school can have only one principal, this is a one-to-one relationship. The next type is a one-to-many or a many-to-one relationship. When one entity participates once in the relationship and the other entity participates multiple times, it is a one-to-many or a many-to-one relationship. In this case, it's the same relationship, just expressed in both directions. one school is attended by multiple students, or multiple students go to one school. This is a one-to-many and this is a many-to-one relationship structure. It's the same relationship structured in the flipped around manner. Let's look at this for the example. Multiple students go to one school. Does that relationship make sense? Can we say that only one student goes to one school? No, that doesn't make sense, hence it is not a one-to-one relationship. Can we say the flip side of this? Can we say one student goes to multiple schools? That it does not sound right either. That doesn't make sense either, because one student will not go to multiple schools. But since it is true that one school can have multiple students, or multiple students can go to one school, this is a many-to-one relationship, or in this case, a one-to-many relationship. The third type is a many-to-many relationship. When both entities participate multiple times in the relationship, it is many-to-many. In this example, we have multiple students can take multiple courses. Okay, how can we check the validity of this? One-to-one is ruled out straight away, because we can't have one course for each student that is there. Course is not exclusive to students, so the one-to-one doesn't make sense. Can we say that one student can take multiple courses? Sure, one student can take multiple courses. Can we say the other way around? Can we say multiple students can take one course, or one course can be taken by multiple students? Yes, that is also true. Since this one-to-many relationship kind of goes both ways, we can say that this is a many-to-many relationship where we can say that multiple students can take multiple courses. The next topic is participation constraints. The first example is, or first idea is total participation. If all members of an entity set have to participate in the relationship, it is called total participation. For example, a product that a company owns and has not sold yet has to be stored at some location, at some warehouse, some store, but somewhere. So all products under this product entity have to be stored at a location. It is represented using a double line between the totally participating entity and the relationship. Hence, you see here, all products have to be stored at some location. The other example is partial participation, where we are saying if members of an entity set may or may not participate in the relationship, it is partial participation. For example, an employee may or may not volunteer for a community service event. It is represented just by using a simple solid line between the entity and the relationship, and we are saying that an employee may or may not volunteer for community service. Can we really say that an employee has to volunteer for community service? No, it doesn't make sense, because has to and volunteer kind of contradict each other. Hence, we can say that this is a partial participation example. In summary, we can say that the ER model easily translates real-world systems in a SQL-friendly format with little to no technical knowledge. An entity is a physically or conceptually existing object. An attribute is a property that describes an entity. A relationship shows us how entities are associated with each other. And again, we have the various examples of symbols that we came across when we learned ER diagrams. Thank you very much for listening, and in the next lecture I will be covering entire examples of how we can build an ER diagram using all that we have learned today. Thank you to Geeks for Geeks for having great notes on the topic of ER models, and I have linked the website below in the description. And thank you. Hope to see you all again.